Hi. The next topic we're going to cover is going to concern homogeneous functions. Okay, let's start with the definition. A function is said to be homogeneous of degree r if multiplication of each of its independent variables by a constant j will alter the value of the function by the proportion jr. That is if. And look, what this definition says is that we will call a function homogeneous of degree r if it happens to be that if we multiply each independent variable in the function by some constant j, what we're going to get in return is exactly the same function, but with j up front taken to the power of r. As it turns out, functions like that have very nice properties that we use in statistics, in modeling, in econometrics, and of course, in economics. However, even though this definition is not very complex, the best way to understand this is when we actually see a couple of examples. So let's start with the function f that we have over here. Function f depends on three variables, x, y, and w, and it's given by this formula. How can I check what is the degree of homogeneity of this function, or even if this function is actually homogeneous? Well, all I need to do is to use this formula. So look, instead of writing this function, I'm going to see what will happen to it if I multiply each of its elements by a constant j. So look, here we will have f of j times x, j times y, and j times w. So this means that now in each place, instead of x, I need to substitute jx, y, jy, and w, jw. Okay, so I'm getting that this is jx divided by jy plus 2jw divided by 3jx. Okay, and we can right away notice that actually all the j's here are canceling each other out, right? So what we get is simply x over y plus 2w over 3x, which means that we got the function f. However, look, doesn't mean we do not have any j up front, but doesn't mean that this function is not homogeneous. Actually, it doesn't. Look, I can always write f of x, y, w as j to the power of 0 times f, x, y, w. So actually, this function is homogeneous, and this is a homogeneous function of degree 0. What does it imply? Well, if we have a case like that, this means that a proportional change in each of the independent variables will not alter the value of the function whatsoever. So if I would multiply each of these by 2, right? Actually, value of the function would not change whatsoever. Okay, so this is the case where we say we have a homogeneity of degree 0. Okay, so let's try a different function. So what if we've got a function like h, g, and the function is also of three variables x, y, and w, and this one is given by x squared over x plus 2w squared over x. Okay, and look, in this case, we need to do exactly exactly the same thing. In order to check whether this function is homogeneous and what is the degree of homogeneity. We need to, in function g, instead of x, we should use jx, instead of y, we should use jy, and instead of w, jw, which gives us jx to the power of 2 divided by jx plus 2jw squared over jx. Okay, and look, I know this is not something we actually need to do, but let's do it very slowly. Let's multiply everything out and let's take it to appropriate powers. So we've got j squared x over jx plus 2j squared w squared. Here squared and jx. Okay, again we see that some things are canceling each other out. This time squares when j is in the numerator with j is in the denominator. So we see that we've got j in each of these components. So we can take j out of the parentheses. Okay. Now we can see that one more time we circle back to our original function, which tells us right away that we find that this function is homogeneous, and of course in this case j is taken to the power of 1, which means that this time we have homogeneity of degree 0. Or what we call linear homogeneity. So this function is exhibiting linear homogeneity, basically. And this result is the most useful one in economics. Look, in this particular situation, we see that if I double variable x, double variable y, double variable variable w, right, j equal to 2, I will double the value of the function. This is something you hear in economics very often. This is a type of a function that exhibits constant returns to scale. If I double the capital, double the labor, and double the land, I will double the level of production my company is making. Okay, let's see one more case over here. Okay, the last case we're going to discuss is going to be function h, also a function of x, y, and w. And this one is given by 2x squared plus 3yw minus w squared. And look, again, if I want to see the degree of homogeneity of this function, I substitute x by jx, y by jy, and w by jw. And let's see what we get. Look, from this one, we get 2j squared x squared plus 3j squared y, w, 1j from each of these letters, and finally j squared w squared, which gives us j squared, a common component in all the terms that we see over here, times 2x squared 3 plus 3yw plus w squared, which brings us back around to our original function. And as you might guess, in this case, because the power here is 2, we would call a function like that homogeneous of degree 2. Because if this would be a production function, it would mean that if I double the labor, double the capital and double the land, I will actually have 4 times as much of production, right? Very unrealistic scenario of increasing returns to scale. However, still mathematically possible. Okay, and look, homogeneous functions are exhibiting these properties. They're extremely useful, as we said, in econometrics and in economics. So we're gonna study them a little bit closer. However, we will, for now, focus our attention only on the linear homogeneity, so on homogeneous functions of degree 1, and properties of this type of function are going to be discussed in our next video. Take care.